Welcome. My name is Erick García from Trinnoverse Research, and in this presentation I will share with you a strategy designed to reduce token usage in large language models. This work was presented at International Conference on the AI Revolution, Research, Ethics and Society, 2025, and explores how sequential NLP and data cleaning techniques can optimize prompt efficiency without compromising output quality. Token-based pricing in large language models increases cost as prompts become longer and more verbose. Reducing input size directly improves processing speed and reduces computational expense. By applying a series of pre-processing steps, we can eliminate noise and compress the message, making it easier for the model to process while reducing token consumption. Our approach achieved up to 65% token reduction while preserving output quality. This study introduces 4 key contributions. First, a sequential preprocessing strategy to reduce token usage in LLM prompts. Second, the definition of a phenomenon we call the text-to-token compression paradox. Third, an empirical evaluation across 3 OpenAI models, GPT-4, GPT-4o Mini, and GPT-3.5 Turbo. And fourth, a demonstration that this strategy can reduce token count by more than half, while maintaining the semantic intent of the original prompt. Language models don't process words as we see them. Instead, they break input down into tokens, which are subword units. The number of tokens affects latency, memory usage, and cost. This process also introduces inconsistencies and inefficiencies. For example, a sentence with 33 characters might yield only 8 tokens, but small changes can cause token counts to increase significantly. Understanding this behavior is key to designing better prompts. Prompt verbosity leads to unnecessary token consumption. There is currently no standardized pipeline to compress prompts efficiently. More importantly, token count is not always proportional to the number of characters. For instance, a sentence might be shortened in appearance, but generate more tokens depending on how the tokenizer splits the text. This creates a trade-off. We want to compress without losing clarity or context. The Sequential Text Compression Strategy, or STCS, is a pre-processing pipeline that reduces token usage before a prompt is submitted to a language model. It applies multiple compression techniques in a specific sequence, using both NLP and data cleaning tools. The goal is simple: to minimize the number of tokens while preserving the semantic intent. STCS operates independently of the LLM engine and can be adapted to different domains or use cases. STCS integrates 2 categories of compressors. The first includes natural language processing techniques such as stemming, lemmatization, text abbreviation, and frequent word replacement. These transform language elements into simpler, more compact forms. The second category focuses on data cleaning, stop-word removal, normalization, and duplicate elimination. Combined, these tools allow for scalable, modular preprocessing tailored to each input. Let's look at a real-world example. The initial message is, "Hello, good morning. I'm writing because I want to schedule an appointment with the doctor next week." This input is tokenized into 20 tokens. When analyzed by the model, it is correctly interpreted as a polite, healthcare-related request with moderate urgency. This serves as our baseline for measuring compression effectiveness. We begin compression in 3 stages. First, we apply text abbreviation, transforming words like schedule and appointment into sked and appointment. Interestingly, this increases the number of tokens to 24, an example of the compression paradox. Second, normalization removes punctuation and applies lowercase formatting, reducing the count to 19. Third, stop-word removal drops the token count to 11, while maintaining the intent of the original message. In the next stages, we continue refining the message. Synonym replacement has no impact on token count in this case. Frequent word replacement simplifies terms like good morning to hi, reducing the count to 10 tokens. lemmatization does not further reduce the count but improves interpretability. Finally, removing duplicate greetings results in a clean message with only 9 tokens. At this point, we've compressed the original message by more than 55%. After reaching the final compressed prompt, we tested its effectiveness across 3 major language models: GPT-4o Mini, GPT-4, and GPT-3.5 Turbo. Despite the reduced token count, all models correctly interpreted the user's intent, tone, context, and urgency. GPT-3.5 Turbo delivered 100% accuracy across all metrics. This confirms that significant token compression does not degrade LLM comprehension when preprocessing is properly applied. This graph shows how token count decreases at each compression step. We started with 20 tokens, peaked at 24 due to abbreviation, and ended with just 9. That's a 55% reduction using the basic strategy. By improving implementation, such as removing filler words like hi or applying more aggressive lemmatization, the compression can reach up to 65%. In total, the character count dropped from 101 to 39, while preserving full interpretability. Compression, however, comes with trade-offs. Overcompressing a prompt may strip away critical keywords and reduce clarity, forcing the model to ask for clarification or misinterpret intent. There's also the compression paradox. Reducing the number of characters doesn't always reduce the number of tokens. For example, next week creates 2 tokens, while NX to WK creates 3, because of how subword tokenization behaves. This illustrates the need to compress strategically, not blindly. In conclusion, the sequential text compression strategy is a simple, modular, and effective way to optimize token usage in language models. It achieved up to 65% reduction in token count, confirmed across multiple models with high reliability. Future work includes adaptive compressors that respond to input length or domain, multilingual testing in languages like Chinese or Indonesian, and heuristic-driven selection to dynamically order compressors for maximum efficiency. If you'd like to learn more, the full research and implementation code are available on GitHub at github.com/Trinnoverse. For contact or collaboration, feel free to reach out at trinnoverse@gmail.com or visit trinnoverse.com. I look forward to connecting.